Here we are again. Last time I started talking about kriging and all of the assumptions that go into kriging in order to make it proper. So this time I'm going to do an example. This example is one of the counties in Utah, Sevier County. What you see here are all the points that the GNIS, or Geographic Names Information System, has for that county. And the GNIS takes elevation information from the NED dataset, National Elevation Dataset, and assigns elevation values to all of these places in the GNIS. So theoretically, the points that are in here have the same values as this raster, or this higher resolution raster dataset, has at the centers of the cells. So I'm basically going to do interpolation trying to use this to recreate one of these two things, and kriging is what I'm going to do in the example. Remember, there's a whole bunch of assumptions that you need to be meeting if you're going to use kriging and have it be successful. And there's a toolbar and an extension, I think, in ArcGIS called the Geostatistical Analyst. If you have that extension, you can activate a geostatistical toolbar which has some functionality that lets you explore the data. So I'm going to walk through how you might explore the data to see whether it meets these assumptions that kriging needs to see. Normally distributed. Remember, bell-shaped curve, mean, median, same diff. You can check that with a histogram. And this doesn't really look like a bell-shaped curve to me, so excuse me. Maybe our input data doesn't follow a normal distribution. But remember, you can transform your data sometimes to make it look like a normal distribution, and so that might be something we should consider when we do the kriging of this elevation data, is to transform it. What else can you do to check at normal distributions? You can do what's called a QQ plot, and what a QQ plot does is it plots the actual values. These are the actual values of our elevations on a chart that shows you what normal distribution would be as a straight line. So this straight line is what a normally distributed data set would look like, and these circles are our actual data. And you can see that at the very ends we have data that are out here quite a ways away from the normal distribution line, and the same way up here. These are outliers, and so these are elevations that are abnormally high or abnormally low compared to what a normal distribution of elevation values would be. What you can do with this exploratory tool is you can use the cursor. I don't have it activated now in ArcGIS, but you could select maybe these points from this QQ plot, and you could look at the map, and those points would be selected on the map. So you could see actually where the physical outliers are in your data. Global trends. How can you check for trends in your data set? Well, you could do some trend interpolation, or you could use this trend analysis exploratory tool that allows you to look at your points. You can kind of see these in the light green here. You can actually add sticks to the points to show kind of the equivalent of a bed of nails of your points, but I've taken the sticks out of here. And you're looking spatially at the points, and it's projecting trends into these planes. So you can see there's a linear trend, and there would be in the Sevier County from west to east. It's lower in the west and higher in the east. And then there's a second order trend here from north to south. And so using this tool, and you can move this around and rotate it and look at it from all dimensions, you can see if there are trends. If there are trends, you need to transform your data before you do kriging. What about stationarity? Remember, that's where the difference between values just depends upon the distance between the points and not on where you're at in the map. You can use this Voronoi map, and you can look at this map, and what you end up seeing here is that in some areas, like the dark areas, the difference between values at short distances is much higher than the difference between values in the light areas. And so you have some non-stationarity. It's not bad, but there are a couple of areas in your map that have some non-stationarity problems. Spatial clusters, that's just where the points are. And you can imagine, since we're using the GNIS points, and the GNIS points are places, there's going to be a lot more places located close to populated areas. And so there are probably a lot of places around this town right here, schools, parks, landmarks, things like those. They all count as places. So when you make a density map, you're going to be able to see where these things may cluster. And I'll talk more about clusters in a later video when we do some spatial statistics. If you have clusters, you need to decluster your data, which is basically going to give the points that are close to each other smaller weights in the interpolation so that the number of points doesn't outweigh the interpolation by just being so many points. Spatial autocorrelation, remember that's the difference between values of points plotted along an axis which is the distance between the points. And you can see in this case that there appears to be, kind of like Tobler, the difference between values for points that have very low space between them is very small. Points that are close together are similar. Points that are further apart are values that are further apart. So you can see that there's spatial autocorrelation. Beyond a certain point, you can see that the points are all over the place. And you can imagine these points up here are relatively short distances between them, but they have a lot of difference between the values. So these might be low elevations that are located next to high elevations. And just like in these other exploratory tools, you can select the points on this chart and it will select the points in the map, and you can go look at your map and see where these points might be. Okay, so we've got all these assumptions. How about for this example? Continuous, yes, elevation is continuous. Normally distributed, not really, but we can probably transform it. Global trends, it looks like there's some trends, so we're going to need to detrend before we do our kriging. Stationary, close but not exactly there, so that one's going to be marginal. Spatial clusters, you can see there are a few clusters, so we're going to need to decluster before we do our kriging. And we saw some autocorrelation. So it looks like we've come close to meeting all the kriging assumptions, or we can do transformations that get us there, so we're going to go ahead and do kriging. Okay, so what we want is an output surface that looks like this, and when we do kriging we get an output surface that looks like this. And you can see that this is a pretty good interpolation. This is a pretty good approximation of what we'd like to get. So kriging is working pretty well here. So that's just with the basic default assumptions. Now we can also transform things by trying to make our curve a bell-shaped curve, and we can detrend things and then do the kriging on the transformed detrended points, do the kriging, and then go backwards in the transformation in the trending. And we get this. It looks kind of the same, but maybe it looks a little bit better, not sure. Okay, we can transform, detrend, and decluster, do the kriging again, and we get this. Again, it's kind of hard to tell visually whether this is better than either of the other ones. But what you can get when you do kriging is you can get statistics, and you can get an estimate of how much error there is in the kriged interpolation. And so how do we know which one of these is best? It's kind of hard to tell just looking visually at the interpolated surfaces. But kriging also gives you an estimate of the errors, and these are called the error surfaces. And so for each one of these approaches that we took to kriging, we get a different error surface. The darker reds are higher errors, and the lighter colors are lower errors. So obviously, looking at the error surfaces, it looks like this third method gave us the best kriging. Even though you can't really tell from this, you can tell from your error estimates. You can get numerical estimates of the errors. So the first one we got, the estimated mean error is 372 meters. When we did the transformation and the detrending, our mean error goes from 372 meters down to 134 meters. And when we do the declustering, detrending, and transformation, our mean error goes down to 90 meters. And you notice that the standard deviation goes up from the second one to the third one. So we get more variation in our error, but we get a lower mean overall. So if we do the transformation, the declustering, and the detrending, we're going to get the smallest estimated error, and that's going to be the best kriging that we've done in the three methods that we've tried. You can mess with your models and do all kinds of things with kriging to try to hone in on a really good interpolation, and you can see where there's a lot of power there. Okay, interpolation in general, I've given you 5 different ways to do it now, so there's some generalizations you can draw about interpolation. If you got a lot of points and they're uniformly distributed, all 5 of them are going to do a pretty good job. If you got clusters or there's large gaps between the clusters, most of these methods are not going to do a good job. So no matter what you do, you're not going to get a good interpolation. And most of the methods are going to underestimate the high points and they're going to overestimate the low points. They're going to cut off the peaks and fill in the valleys. Okay, so that's enough of that interpolation stuff. We need to talk a little bit more about some other spatial statistics, some descriptive statistics you can do to help you describe spatially what's going on with your data, and some inferential statistics that help you make decisions about whether your data are clustered or whether there are hot spots or cold spots in your data. So that's what the next couple videos will be about.